In this video, we'll be looking at section 7.3, which is volume with the shell method. So in this section, we're also going to be looking at trying to determine the volume of a solid of revolution using the integral, but now we're going to be using a method called the shell method as opposed to the disk or washer method. So the shell method is an alternative method for finding a volume of a solid of revolution that uses cylindrical shells, or I like to think about it like hollow tubes. All right, so now let's consider the following rectangle and its axis of revolution. So we'll say this is our axis of revolution. And we'll say this is our rectangle. All right, so we're gonna revolve it around our axis of revolution. Go ahead and fill it in. All right. And we're going to call the width of the rectangle W, right? So this is the width. This is a rectangle that's on its side, right? So this would be the height of the rectangle. And something that might seem a little bit strange, but will come in handy later, is we're going to call this distance P, the distance from the center of the rectangle to the axis of revolution. So you could imagine taking this horizontal rectangle and revolving it around the axis of revolution. I get this nice tube that is hollow, right? That has a hole in the middle. Okay, so let's go ahead and try to draw this tube here on the next slide here. So I'm drawing it here. So our tube looks something like that, right? This is our original, this is our original rectangle that I have revolved around the axis of revolution here. This was our axis of revolution, and I get a tube, right? How thick is that tube? Well, the tube has a thickness W, and it has a length H. So the outer radius of the cylinder of the shell, right? Because we think about this big hollow tube, right? How do we, if I was going to try to find a volume of it, well, I would need to find the volume of the entire thick full shell with no hole in it, and then I need to subtract the center, right? The volume of the center, and that would give me the volume of the hollow tube or the shell, right? So the radius of the outer cylinder is going to be, it's not just P, right? Because I need it to go from the axis of revolution all the way up here to the top of the rectangle, right? So it's going to be P, and not P plus W, but P plus W over 2, right? Because W over 2 is this distance right here, right? So the outer radius is going to be P plus W over 2. The inner radius is going to be P minus W over 2. Right, for the same reason. So if I want to find the volume, I'm going to do my side work here, the volume of the hollow tube, right, the shell, I need to do the volume of the full, or let's say the outer, right, the full thick tube with nothing missing, minus the volume of the little hole in the middle, right, or the inner cylinder there. And that will give me the volume of just that outer shell, right? Just that tube. Well, what's the volume of the outer? Remember, in general, the volume of a cylinder is going to be pi r squared times h. So in this case, it's pi. What's my radius? We just found that to be P plus W over 2 squared. And what's the height of this cylinder? The height is given by h. Minus, now we'll find the volume of the inner tube. So it's going to be pi, and now what's that radius? Well, that's P minus W over 2 squared times, again, the height of the cylinder, which is h. Now, if I multiplied everything out, if I squared everything out, I'd end up with this formula for the volume, which is going to be 2 pi PHW. Right? Okay. So let's think about what we did in the case where I had disks and washers. Remember, I had the solid of revolution, and I added up infinitely many disks inside of there. Or actually, I put n of those disks in there, and then I took the limit as n goes to infinity, right? And that gave me the volume of that shell. Same thing here, right? If I have this if I have this solid of revolution and I want to find its volume, well, I can take a bunch of these hollow tubes and I can put infinitely many inside that solid of revolution, and that will give me the volume of that solid of revolution, right? So if I take a bunch of little tubes with small radius and a bunch of tubes with big radius and I add them all up, I'll eventually get the volume of the entire solid. All right, so again, that's why I'm using the integral. So I'm adding infinitely many of these shells inside of the solid of revolution, right? So this formula right here is going to be the formula that I'm going to take infinitely many of these volumes, right? So infinitely many means the integral, right? So that 2 pi here, if I wanted to have my formula for the shell method, I'm going to use 2 pi, and then I'm going to do the integral from c to d. And then now I do p of y, because p is going to be a function of y in this case, and then h of y, because that's going to be a function of y in this case as well. And then that w is actually going to end up being the width, right? That's what it stands for. And remember, the width is like the delta y. And then when I take infinitely many, when I do that limit to get the integral, it turns into a dy. So this is my formula if I have a horizontal axis of revolution for the shell method. So let's go ahead and draw my picture of what's going on here. So this is my horizontal axis of revolution, right? And then let's draw the shape that I'm going to revolve around the horizontal axis of revolution, right? My starting y value is going to be c. My ending y value is going to be d. So this is the area here that I'm going to revolve around my axis of revolution, right? You can imagine what that solid would be if I revolved this around our axis of revolution, right? So now let's draw what my rectangles look like in this case. So my rectangles, remember, they're going to be horizontal rectangles, right? I have a horizontal axis of revolution, so I put horizontal rectangles there. So notice now the width here is going to be delta y, right? Because it's a change in y values, right? That's why this is a function of y if I have a horizontal axis of revolution. This distance right here is h of y, right? That's the height of my rectangle. And this distance from the center of my rectangle to the axis of revolution, remember, is my p of y, right? So it's a little bit awkward. I have a horizontal axis of revolution. Horizontal, we normally think of x's, but actually in this case, the horizontal axis of revolution means that we integrate with respect to y. So now in the case where I have a vertical axis of revolution, right, we haven't drawn any pictures of this yet, but we will here. If I have a vertical axis of revolution, my formula actually changes to be a function of everything is functions of x, right? So I have p of x and h of x. So in this case, I now have a vertical axis of revolution, right? And let's say that my solid looks like this, right? And then this is going to be my solid here. I'm going to revolve it around this vertical axis of revolution. So this is my starting x value. This is my ending x value, again, because those are on the x-axis here. And now if I'm going to draw my rectangle, this time my rectangle is actually going to be a vertical rectangle, right? And so notice that the width now is going to be delta x because it's going to be x values that are changing. This height now is going to be h of x. And this distance from the center of the rectangle to the axis of revolution is going to be p of x. Right? Okay, so now let's go ahead and do a couple examples of using the shell method. Right? So let's find the volume of a solid form by revolving the region bounded by y equals x cubed, x equals to 0, and y equals x about the x-axis. Right? So notice our axis of revolution is what? Our axis of revolution, where are we revolving this, is the x-axis, which is horizontal. Right? So using the shell method, if I have a horizontal axis of revolution, I know I need to integrate with respect to y. I know I need a horizontal rectangle and I know I need to integrate with respect to the variable y. All right, so let's keep that in mind when we're drawing our picture here. So here is my picture. We're going to draw y equals x cubed, right? That looks like this function here. This is y equals x cubed. And then we need to draw y equals 8. That's a horizontal line at the y value 8. So we'll draw that right here. We'll say this is 8. This is y equals to 8. So that's the, and then we want to have the solid bounded by y equals x cubed, x equals 0. Remember, that's the y-axis and that line. So the area that we are bounding is this piece right here. And we want to revolve it about the x-axis, right? So we are revolving it just like this. Right? So again, I need my rectangles to be horizontal. All right, so my rectangles are going to look like this. And since I'm integrating with respect to y, I need my function y equals x cubed to be in terms of y. So if I were going to solve this so that it's x equals y something, 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 so that way my function's in terms of y, this means that x equals the cube root of y, right? So I can go ahead and change this right here and write this as x equals the cube root of y, since that's the function we will be using because we want everything in terms of y. Okay, so now I need to figure out my pieces, right? My formula says that I need to find C and D, my starting and ending points. I need to find P of y and H of y, right? P of y, remember the distance from the center of the rectangle to the axis of revolution, and H of y being the height of the rectangle. So start and finish are easy, right? Where do I start? I'm starting right here, which is 0, and I'm ending up here, which is the y value 8, right? So C and D are easy. Now we need to figure out what P of y are and what H of y are. And we're going to figure that out by looking at the rectangle. Right? So again, this is delta y because we're changing y. Now the H of y is going to be this right here. Right? That's the height of the rectangle. Notice that if I would have drawn my rectangle a little bit higher, a little bit lower, my height of that rectangle would change given by whatever that function, the purple function is. Right? So the purple function gives us the height of that rectangle, right? So that means that P of y is going to be, nope, not P of y, H of y, the height of our rectangle. Is H of y, right? It's a function of y, and it's going to be the purple function, right? The cube root of y. The distance from the center of the rectangle to the axis of revolution. What's our axis of revolution in this case? The x-axis is, now let's think about this. So the center of the rectangle, so there, all the way to the x-axis. Well, notice that that is actually, that's going to be our P of y here. That is going to be that distance right there is going to be y. And I'll explain why here in a second. So P of y in this case is going to be y. Well, why is that? Well, in order to get the height of my rectangle, right, I need to plug wherever I'm at here, whatever y value I'm at here. If I'm up here, if I'm down here, I need to plug that y value into my function x equals the cube root of y. And that will give me my height. So wherever I was here gives me my height of my rectangle. Well, wherever I was is actually the y value that I'm plugging in, right? So that's why, and it's a variable, right? It changes depending on where I'm at on this axis, right? So that is why P of y is going to be y. So now it's just a matter of our formula, right? The volume is equal to 2 pi, the integral from c to d of P of y times h of y, dy. Well, in this case, 2 pi, and then c and d are our starting points, so we know we were going to go from 0 to 8. P of y, in this case, what do we say P of y was? Is y. H of y is going to be the cube root of y dy, right? So 2 pi, the integral from 0 to 8. Remember that the cube root is y to the 1/3. So if I multiply y times 1 to the 1/3, I'm actually adding their exponent. So I add 1 plus 1/3, which gives me y to the 4/3 dy. And now if I solve that integral, I end up getting, off the top of my head, I don't know. Sorry. 768 over 7 pi. Right? Okay, so now let's look at when I have a vertical axis of revolution. So let's find the volume of a solid form by revolving the region bounded by y equals x minus x cubed and the x-axis about the y-axis, right? Okay, so here's my function. Now, if I were to go to Desmos and I do x minus, what's my function here? X minus x cubed, all right? X minus x cubed, right? It looks like this. And we're focusing on this portion around the origin because we want it to be bounded by the x-axis, right? So my function x minus x cubed looks something like this. All right, so this is y equals x minus x cubed, and I'm going from x equals 0 to x equals to 1. Notice x equals to 1 is where I actually cross the x-axis here. So we can see that this point right here is x equals to 1. Here's x equals to 0. And let's draw the region that we want here. Is going to be this piece right here, right? And we want to revolve that about the y-axis, right? So in this case, our axis of origin is what? It's the y-axis, right? Which is vertical. So what does that mean? That means I need vertical rectangles, right? Because in the case here, where if I was looking at the vertical axis of revolution, I need vertical rectangles, right? And which means I need to integrate with respect to x, right? So in other words, my functions in terms of x, life is good. I can leave it like that. Okay, so vertical rectangles. So my rectangle needs to look something like that, all right? So the width of my rectangle is still going to be delta x because it's the change in x there. The height of my rectangle, right, is right here. This is h of x. If you notice the height of my rectangle, if I shifted that rectangle to the left or the right, the height of that rectangle is going to be given by the purple graph, right? So the height of the rectangle is given by h of x equals to the purple graph, which is x minus x cubed. Now we need p, right? P is the distance from here to here, right? That's my p of x. It's a function of x. Once again, how do I find the height of that rectangle? Well, I go to where I am on the x-axis, I plug it in, oops, I go to where I am, say I'm right here, I plug it in, I get the height, right? So I go here where I'm at, I plug it and get the height. So what is that distance? That distance is going to be x. So the distance from the center of the rectangle to the axis of revolution, which in this case is the y-axis, is p of x equals to just x. In general, if my axis of revolution is either the x-axis or the y-axis, oftentimes p of x or p of y is just going to be y or x, right? In the case where my axis of revolution is some other line, that's where I need to be more careful, right? But if the axis of revolution is the x-axis or the y-axis, then it's very simple, right? P of x is either equal to x or y. Okay, so now it's just a matter of our formula. Volume equals 2 pi, the integral from a to b, p of x, h of x, dx, 2 pi. Again, where do we start and finish? We start at 0, we end at 1. P of x is x. H of x is x minus x cubed dx. 2 pi, the integral from 0 to 1 of x squared minus x to the 4th dx. And if I were to compute that integral, I would get 4 pi over 15. All right, we'll go ahead and end this video here.